Hello everyone. So this video is going to be all about converting an epsilon NFA or an E-NFA to a DFA. Back then we had another conversion from from just NFA to a DFA using subset construction. Now this will be quite different, but there will be subset construction in some way, but it's a bit complicated than the previous one. In the previous one we just did union operation, but here it's a bit complicated. We use e-closure. So at the beginning, in the beginning step, we will have an E-NFA diagram given, or if not, then there will be a transition table given, and from that you could convert that to an E-NFA, and the E-NFA diagram has to be drawn properly. In the last one, where we had to convert an NFA to a DFA, we just used the transition table. No matter what was given, the transition table was the main data that we needed. So even if in the question it was just given that it was just only the NFA diagram was given, we would have to convert it to a transition table eventually. But in this case, you need the state diagram more compared to the transition table. You actually need just the state diagram. Right, so in the first step, we find the e-closure of all the states from the NFA, and then after that we draw a transition table. And in that transition table, we start computing the DFA table. That is the transition table and the DFA table are one in the same. And we start computing from the first state of the e-closure, and then take the resulting states that we get, and later on we use that resulting state as the next state to compute. This part is similar to the NFA to DFA conversion. We took the states that we got in the right side, and we started taking those states and then computed the next state transition after taking those states. So you'll understand after I start computing. So this is the question given. In this question, you could see that 0 holds star. So as you can see, epsilon in the beginning, epsilon in the end, epsilon directly to the final state, and epsilon in the middle going back. And 1 0 is a concatenation, so 1, then epsilon, then 0. Right. So let's compute the e-closure for all the states. There are 6 states, 1 2 3 4 5 6. So we compute the e-closure for all states. What is e-closure computation? It's basically finding out from this. Suppose we are computing the e-closure of state 1. All right. Then we find, so for this we find out from state 1 which state does it go next, using the epsilon transition. So from state 1, using epsilon transition, we go to state 2, we could go to state 6, and we could also go to ourselves. So this is a rule, this is a convention, this is just a hard and fast rule that you would need to know, that using epsilon transition, it goes to the states that are given in the diagram, and also it goes to itself. So it would go to itself no matter what, even if there are no epsilon transitions given. So for the e-closure of 1, we get the states that we go to are 1, 2, and 6. These are the set of states. Now let's compute e-closure of state 2. For state 2, we don't go to any transition, we don't go to any state using an e-closure transition or using an epsilon transition, so it will only go to itself. So then for state 3, for the e-closure of state 3, we always go to itself. The state for state 3 will definitely go to itself, and it goes to state 4, as you can see from here. And then e-closure of state 4 is, it goes to itself, as we know, and that's it. It just goes to itself, it does not go anywhere else. And e-closure of state 5 is, we go to 6, we go to 2, and then we go to itself. So 5, 6, and 2. So let's write it chronologically: 2, 5, and 6. And for state 6, we go to it just goes to itself. So 6. Now let's draw the next step is to draw the transition table. Let's recall. We find the enclosure. Fine, we did this. This step is done. And then we draw the transition table. So how is the transition table drawn? These are the inputs, 0 and 1. So 0 and 1 are the inputs, and we always start from the first enclosure. We always start from the first enclosure state. So 0, 1 is the input. So what's the first enclosure state? It's 1, 2, 6. This is the first state. So recall that in a DFA, this set of state is always considered one state. You can't have multiple states in a DFA. DFAs are not so ambiguous diagram. It's a really specific diagram. So 1, 2, 6, right? So on input 0, where does state 1 or state 2 or state 6 go to? On input 0, state 1 goes nowhere. On input 0, state 2 goes nowhere. And on input 0, state 6 goes nowhere. So phi or empty set. On input 1, where does state 1 go to? Nowhere. Where does state 2 go to? 3. And where does state 6 go to? Nowhere. But as you can see, in state 2 goes to, on input 1 it goes to 3, but it could also go to 4 because it has an empty transition here. So it can reach both 3 and 4. So 3 and 4 will be one state. 3 and 4 we found it here once, so it could be considered one state. Right, so what are the new states that we got in this? I suppose this is one iteration or something. On the first iteration, we get this. So what is this new state that we get here? 3 and 4. So we place 3 and 4 on this left hand side, and then we compute what we will get. What is the transition on input 0 and 1? On input 0, 3 goes to it just has an epsilon transition. We can't take that. If it was just 0 and then an epsilon transition, we could take both the states. But since it's just an epsilon transition, then we can't take that. From state 4, it goes to 5, right? And then it goes to 6 too because of epsilon transition. Now, suppose this was something like epsilon was here and 0 was here, okay? Suppose. If this was the case, instead of these and this, then we could not have taken this either. We could not have considered that from state 4 on input to 0 we could go to state 6. Nope, that's not the way. But since it's just we encounter 0 first and then epsilon, we could take both of these states as a transition, right? So from state 4 on input 0 we go to 5, we go to 6, and we also go to 2 through 5. So through 5 we go to 6 and 2. So so what we would, like I said, in a DFA would have to consider each of this one state, so we use a third bracket. So 2 through 5, 6 through 5, and 5. So 2, 5, and 6. We did get the state here in the enclosure, right? And on input 1, we go nowhere because 3 on input 1 is epsilon, and input 4 and 1 on input 1 from 4 we go nowhere. So phi. Now what new state did we get in this second iteration? 2, 5, 6. 2, 5, 6. So 2, 5, 6. From 2 we on input 0 we go nowhere. From 5 on input 0 we go nowhere, and from 6 on input 0 we go nowhere. So 5. On input 1, from 2 we go to 3, and from 5 we go nowhere, and from 6 we go nowhere. But from 2 we could also go to 3 and 4 because 1 and then epsilon. If it was epsilon and then 1, we could not have taken it. We could not have put anything here. But since it's 1 and epsilon, we encounter 1 first and then epsilon, we could take state 4 also. So this is the third iteration. So we didn't get any new state here. It's just 3, 4. 3, 4 we've already computed in the left hand side. 2, 5, 6 we were computed here. 1, 2, 6 was the first initial one. So this is the resulting transition table. From this transition table, we just draw our DFA. So now let's get on to drawing our DFA. So we have three states: 1, 2, 4, 3, 4, and 2, 5, 6. So 1, 2, 6. Now what is the start state? This is the start state. And what is the accepting state? 6 is the accepting state in the NFA. So wherever we have 6 in the set, we consider that an accepting state. So this is the start state and an accepting state. This is also an accepting state. 3, 4 does not have 6, so this is not an accepting state. So this is both a start state and the accepting state. So we have to draw the starting arrow, and this is also the accepting state. And on input 0, it goes to the dead state. So let's draw a dead state. On input 1, it goes to dead state. On input 0, it goes to 3, 4. Right. And 3, 4 on input 0, it goes to 2, 5, 6. 2, 5, 6. This is also an accepting state. So double circle. Sorry for the diagram. I know it looks ugly, but whatever. So on 3, 4, on 0, we go to 2, 5, 6. And on input 1, we go to the dead state. And 2, 5, 6 on input 0 goes to the dead state. And on input 1, we go to 3, 4. Right. So that's the resulting DFA that we get: 1, 2, 6, 3, 4, 2, 5, 6. These are accepting states, and this is just a normal state, and this one is accepting and the starting state. So that's about it for the conversion of an NFA or of an epsilon NFA to a DFA. Let's look at the algorithm again in order to recall. So what is the first step? We find the enclosure of all the states from the epsilon NFA. And then after that, we draw the transition table, the DFA transition table, and we start comparing the DFA table from the first state and then take the resulting states as the next state in each step. So yeah, that's about it for epsilon NFA to DFA conversion. I hope you understood the concept, and please like and subscribe to show more support for this series, and